Consider one example of low pass filter design where the design consideration is given like that. So 3 dB cutoff frequency is 400 megahertz. However, this filter should provide 20 dB of attenuation at 1000 megahertz. And this design needs to be done through the maximally flat procedure, which is also called a Butterworth filter, whose PLR, like power loss ratio, is defined with this expression, where K is a proportionality constant, omega is the frequency, this is the cutoff frequency that we have here as 400 megahertz, and N decides the order of the filter. So we have seen in the previous classes, like we can calculate the G parameters. Those G parameters can be related to the inductance and capacitance in the network to realize a filter. So before beginning to calculate these G parameters, first we need to decide the order of the filter based on the given design consideration. So the first step for solving such a problem, we need to calculate the order of the filter. So we have given some hint here. So at 1000 megahertz, we have a PLR expression here. So how we can calculate the order of the filter? So let's do precisely. If we take the log of this expression, so this order of the filter can be expressed. So this omega is 1000. If we put as 1000, then this PLR gonna be 20 dB. So if we solve this equation by assuming this PLR to be 20 dB at omega equals to 1000, and omega C we have as 400 megahertz. So if we solve this equation, so this is 2 log 10, this is 400, sorry, this is 1000 divided by 400. So this is going to be log 10 99 divided by twice into log 10, it's like 2.5. So this approximately, if we see what this value is approximately 2.51. So this, whenever you see a real number here, so you need to choose an integer value which is slightly greater than this to achieve this performance. So we have chosen n equals to 3 because the order of the filter with this equation comes out to be 2.51. So n equals to 3. So now we need to calculate the G parameters. So the order of the filter is like 3. So G0 and G4 are directly 1 with this kind of formulation. So we need to calculate G1. So G1 would be twice sine of k equals to 1. So 2 minus 1, 1 pi by 6. G2 twice sine, again we have to put 4 minus 1, so 3 pi by 6, and we need to calculate the another G expression, which is sine 5 pi by 6. So sine pi by 6, sine pi by 6, we know that it's 1 by 2, so it's gonna be 1. Similarly, this gonna be 1 and this gonna be 2. So now we have G parameters. These G parameters can be related to an equivalent network So this is source. So suppose this is our G1, this is our G2, this is our G3, and here we have, so G0 is equals to 1, this is equals to 1. So if we choose this as like unnormalized value, so we can replace this as 50 ohm system impedance, 50 ohm system impedance, and these all are normalized values. So G1 is equals to 1, this is equals to 2, this is equals to 3. So right now we have all the normalized values for these components in this network. So now we need to perform the frequency scaling, because all these values are on the normalized frequency. So we need to translate these values to the with the kind of this cutoff frequency. So in this configuration we have assumed that our cutoff frequency is 1. So we have the normalized values for these reactants. Now we need to translate to the frequency omega c equals to 400 megahertz. So how we can do that? So these is like here C1 equals to C3. We have seen like this is C1 and this is C3, this is L2. C1 equals to C3, both are equals to 1. So this would be G divided by omega C into the characteristic impedance. So characteristic impedance is our Z0, which is equals to 50. So this is called the frequency and impedance scaling. Similarly, the L2 would be G, this is G1 also, and it could be 3 also. G2 into Z0 divided by omega c. So now we need to put these values to get, say, C is equal to 1 and omega c is 2 pi f is 400 into 10 to the power 6 and Z0 is equals to 50. So we need to solve this and we'll get the values for this. So the solution for this is approximately 7.95 picofarad. And if we solve this, say G2 here is 2 into 50 divided by 2 into pi into 400 to 10 to the power 6 megahertz. If we solve this, this comes out to be 39.8 nano Henry. So after this frequency and impedance scaling, we can put the values of these. So the capacitance C1 is 7.95 picofarad. So similarly this also 7.95 picofarad, and this is going to be your 39.8 nano Henry. So the next job is to analyze this. So you can put this problem into the any simulator and you can see whether it's realizing a low pass filter of similar characteristics or not. So you will see something kind of this response. So this would be, so if it is power response or if it is dB, so it would be -3, this would be 0, and this would be around 400 megahertz. So this is the transfer function would be for this filter. So this is the procedure, a generalized procedure to design a low pass filter through Butterworth filter. Thank you.